Hello and welcome to Toddcast 57. This will be the last for the alcohol chapter, chapter 12. And it's going to hopefully summarize a bunch of things, put it all together. But I just want to catch my breath for a moment and realize we have covered an awful lot in this chapter. We've covered oxidation of alcohols, different reactions, covered reduction of ketones and aldehydes and esters and a few other carbonyl-based compounds that can turn into alcohols. We learned about some poison catalysts. We sort of put this whole thing together. So the redox aspect has been a lot, but also we did review of previous aspects of alcohols, their acidity, what you can convert them into to make a better leaving group, some of the other reactions they do. And so this is a chapter, it's probably going to be the first of a few in OChem that'll just pile on so much information that it becomes really, I don't know, really overwhelming. There's a certain anxiousness to it. And so for this chapter, it is imperative that you try to keep track of things in the most organized fashion you can. Classify reactions as you wish. That redox chart going forward and backwards is really helpful. Adding the Grignard aspects is really helpful. But then also connecting it. So those primary, secondary, and tertiary alcohols that we show the redox for also show other reactions you can do. PBr3, SOCl2, OTOS, some of those different reactions. And try as best you can to get organized. And so the book does a really good job at the tail end of offering an overview chart that is both daunting but really helpful. And so I hope to work towards that by the end of this. But for now, last things I want to do is go into a little more details on the oxidation to alcohol reactions that we did. So I want to look at first the chromate reaction. And this is kind of going to be a little out of sequence, but what happens is the alcohol itself attacks the chromium and it forms this chromate intermediate. So the alcohol that goes on, this came from the alcohol right here. This lone pair, and I like this little squiggly arrow, but this lone pair can come and deprotonate, and you end up releasing from the chromate it's bound to. So you take the electrons from this hydride. So this is the H getting oxidized from this carbon. So, like I mentioned, in order for something to undergo, a carbon-based compound to undergo oxidation, you have to have at least one H, this one right here, attached to the oxophilic carbon, this O here. But this O, rather than being the OH like we had before, that O has attacked the chromium and has formed a complex. When this water comes in and deprotonates it, this go here, forms a carbonyl, and it releases from the chromium. This is the reduction part right here. This chromium is getting those electrons. So the chromium is being reduced while this is another bond to O. It's losing bond to H and gaining bond to O. So the carbon is being oxidized by this right here, and chromium is being reduced by those electrons right there. So important to recognize what this breaks into. This is why we need to do it under acidic conditions. When it's aqueous, it can oxidize all the way up to the ketone. Aldehydes can oxidize all the way up to a carboxylic acid. Without water, we limit it. You can only use one H, and there is only one H on the ketone, so it's not that important. But just note then that the chromate is getting reduced through this reaction. Okay, so I want to consider it, and I'm doing kind of out of sequence this way. So that's what we got here. Let's go back and figure out how this actually got on to this chromate molecule. So this H, I want to emphasize, is the acidic H. So this one's going to be the oxidized one. This is the one that's going to lose electrons, as we see down here. That means this is the more acidic proton. So this H right here is going to have to somehow combine with this OH to form water. So if, under acidic conditions, we protonate this OH, if that water can leave, this O can come into chromium, and then it can lose that H as an H+. So this water represents this H+ and this OH, not necessarily combining with each other, but stoichiometrically, we're getting rid of an OH from chromium, we're getting rid of this H from alcohol to form this compound. So here's the alcohol bonded to the chromium. This is the prep work, if you will. This is the actual chemistry I care about. The reduction of the chromium as it gains electrons, and the oxidation of this carbon as it loses electrons from hydrogen and forms a bond to oxygen. Okay, so not a lot to that, but just know that that's your general mechanism. And more importantly, recognize that although I just drew Cr like H2CrO4, You can also do it with a couple different versions. You can do Cr2O7 2 minus. The sodium is just a placeholder. Under acidic conditions, it's going to get protonated. We're going to end up doing the same thing anyway. But the chromate species can come in a few different flavors. So the key thing, when you have a primary alcohol, it has two H's to lose, like we mentioned in that chart. If you have two H's to lose that can be oxidized, you lose the first one to generate the aldehyde. That aldehyde can turn into what's known as a diol, a geminal diol. So now we have another OH capable of adding to the chromate. That can add to the chromate, and then you get one more oxidation up, and you go to this. So you need to have an OH to bind the chromate. So this aldehyde species isn't reactive of itself. The geminal diol it turns into, the two bonds to OH instead of the two bonds to a single O. That's a more reactive species. So this forms this intermediate, which then gets oxidized up. Okay, so because it has two H's, the primary alcohol can be oxidized twice. PCC, where we add pyridine and chlorochromate, so we add a pyridine poison, and we do it in the absence of any water. So we use a hydrophobic solvent, one that will not take on any water. The acid is in the HCl added to the pyridine and the chromate. So this one is a CrO3 combination with HCl and pyridine. It stops at the aldehyde because it cannot form. So normally we think of a compound being able to form the diol to go on to this. With no water present, the pyridine complexing the chromium, that can't occur, so it must stop right there at the aldehyde. So you end up with your PCC being, as mentioned before, HCl, chromate, and pyridine. Okay, yet another way to do this reaction. And I know this is starting to be a little bit overload, but just want you to hang on to these thoughts. So DMP can also carry out the same reaction. There's two H's. It can stop it, but and then also it can react with ketones. So this is also a way to generate just the aldehyde without going all the way to the carboxylic acid. So important to have different ways to do it. On the test, when it comes to anything synthetic, either of these will work. If you put PCC or DMP, perfectly fine. Okay. And then something known as Swern oxidation. Again, I'll take anything. So this is in the book. You'll run into it. I think it comes to a point where we have so many reactions, it starts to be overload. So for synthesis, pick your favorite. The one advantage to this is that it can be done under basic conditions. This can be done under neutral conditions. This has to be done under acidic conditions. And so a greater variety means in like real life situations in lab, you may have a compound that has a basic site you don't want to have react, so you can't use an acid. You have to use one of these other options. But for our testing purposes, for just going through the lecture course, pick your favorite and use it accordingly. So in the presence of water, you're going to go all the way to the carboxylic acid. With PCC, DMP, or DMSO, the Swern combination, you end up stopping. Notice, though, we're doing the ketone. For an aldehyde, you pretty much want to stick to DMP or PCC. Okay, information overload. That's pretty much what this is. So I'm trying to throw last few reactions at you, and those fit on that chart. So if you want to go back and add those, like the Swern oxidation, onto that chart, and just add a few more notes about the way these things work, that will help in your organization. And again, you want to do that for both predict the products and synthesis. Okay, this is where I think it gets a little more interesting. So the biological reactions. So one of the things you're going to learn you learned when you took cell bio, or you will learn when you take biochem, is that there's certain compounds that recur over and over and over in the oxidation reduction region of biochem. One of them is this right here, known as NADH. I've only shown the terminal end where the chemistry really occurs. There's a large amount of molecules still represented by this R, but this works in a way where this red H represents the one that we're going to give away the electrons for. So this is one that's going to cause a reduction over here. So I made it red not because it's acidic, but because it's going to be given off here. When we do this, when these electrons from this N flow over, this pi bond swings over, these electrons can swing out and attack the carbonyl. You're going to end up with a six-membered ring that has a pi bond here, here, and here. And you haven't learned this yet, but that makes it aromatic and extremely stable. Even though there's a plus charge on the end, it's worth it for that aromatic stability, which means this H minus can readily be given away, but also because this is a neutral structure, it can also be picked back up. So at least for now, NADH is going to lose this H along with its electrons. So it is losing an H minus. And so we're going to represent the final molecule as what's known as NAD plus. So again, notice the benzene ring, and I should say aromatic rings, not benzene, because it has to be all carbons. But notice this aromatic ring, 2, 4, 6 electrons in a cyclic, completely conjugated network. That H has been delivered over here, and this O is picked up because now when this comes in, it has to move that pair of electrons because it has 4 bonds now, this will be fifth. So it moves that electron. So I should have represented that also happening. So just to make note, that's going to swing there. So this pi bond is going to turn into a little pair, and you're going to end up with this alcohol and the base, now neutralized, and more importantly, NAD plus. So you end up with, in bio, what they say is NADH going to NAD plus, but you need an H plus here. So typically we represent it as NADH plus H plus going to the reduced molecule that's picked up 2 H's and NAD plus. It is completely reversible. So that's why I'm going to call it redox between alcohols and carbonyls. Alcohols could be oxidized up to a carbonyl using NAD plus. Ketones or aldehydes, carbonyls, can be reduced using NADH down to alcohols. Happens with high frequency. We do a lot of conversion. Okay, so here's the other reaction, NAD plus, complete opposite, the base is going to come in, that's going to go here, move those electrons over. It basically undoes everything we did in the first pathway. So again, NAD plus goes to NADH plus this H plus right there. Absolutely positively have to know this reaction for bio, that concept here. So NADH getting an NADH and H plus reacting, turning into NAD plus, loses an H minus because it lost an H. This is reduction or oxidation, excuse me, my apologies, for the NADH, but it causes reduction. So it causes the carbonyl to be reduced. And once again, do want to apologize because the wording of these, the oxidizing agent terminology can sometimes be a little bit overwhelming and confusing. So this is the reducing agent getting oxidized, causing the organic molecule of interest, ketone in this case, to be reduced. In this case here, this is oxidation of NAD plus. Actually, again, I take it back. So this is oxidation of the molecule itself, but it's through NADH that's actually getting reduced this time. So you always have a redox pair. So if the organic molecule is getting oxidized, losing H with electrons, then the NAD plus must get reduced. You have to couple. If the organic molecule is getting reduced, gaining a bond to H and losing a bond to O, NADH must get oxidized up to NAD plus. These go as a coupled pair. You're also going to learn about electrochemical potentials for both reactions and how this one offers enough energy to overcome whatever this may be, or vice versa, and adds to the favorability of it. I'm not going to worry about it in this class, just have to see the big picture. So if we see it in action, you'll see something like this in your bio courses where, let's say, there's some structure like this, which is similar to the quinone we talked about earlier. 2 pi bonds here, 2 carbonyls here. If this gains an H at one end, then an H plus. So I now made it acidic. So I apologize for the change in color coordination. But if I protonate at one end, then what I hope to see happen, if that goes out and gets H plus, this bond breaks, this bond swings up here, and an H goes to O, and that bond swings over. Completely and utter bizarre that it works out this way, but it does. And I should color coordinate this as being my blue H. This is the one that's going to come from NADH. So that H right there is going to go on right here. That bond is going to swing over. I swung it in opposite way. So I actually had it go here, and that one went up. Really doesn't matter as long as I have a benzene ring or an aromatic ring in the middle, 6-membered ring with 2, 4, 6 pi electrons and a totally conjugated network. We end up gaining the H up here. Here's my red H, my acidic one. And here's my reductive H, my H minus, if you will. So I'm going to call it hydride, coming off of the NADH. So know your biological reactions, not based on the organic molecule, but based on NADH plus H plus being oxidized, giving way to H minus up to NAD plus. If this is being oxidized, it is causing reduction, it is a reducing agent. If NAD plus is going to NADH and H plus, then it's picking up an H minus. It's removing H and electrons, which means it is getting reduced, causing oxidation of the organic molecule. So in this case, NADH going to NAD plus, it's losing its H, so it's undergoing oxidation, which means the other compound must be getting reduced, which makes sense because it's gaining bonds to H. It also had 1, 2, 3, 4 bonds to O. Now it has 1, 2 bonds to O. So equally, you can say it's lost bonds to O. Seeing the big picture, and I keep saying the same things over and over, but hopefully they ring familiar more and more each time. Redox chemistry, gain bonds to H, you've been reduced. Lose bonds to H, you've been oxidized. Gain bonds to O, you've been oxidized. Lose bonds to O, you've been reduced. Okay. Want to do one, I guess, last absolutely major thing that we do in bio and biochem, and that's pathways. So glycolysis is one of those really important pathways you're going to see in multiple bio classes. From a simple OChem perspective, we can think the molecule has been broken down. So when we break things down, that's an oxidative, or in bio they call it a catabolic process. We break molecules down, it's energy generating. So a C6 species known as glucose is going to be reduced to 2 C3 species known as pyruvates. So one glucose is going to go to 2 pyruvates. You're breaking a carbon-carbon bond and replacing it with more bonds to O. So if I look at it, overall picture, I'm going to go from a molecule that starts out with 7 bonds to O. I'm going to generate 2 molecules that collectively have 5 bonds to O each for 10 bonds to O. So I'm going to go from 7 bonds to O to 10 bonds to O. So it's definitely oxidation. So glucose gets oxidized. So the other reagent thing I need to react it with is an oxidizing agent. So if glucose is getting oxidized, then the compound reacted with must get reduced. Reducing agents get oxidized, oxidizing agents get reduced. Because the other compound must get reduced, it is an oxidizing agent. It's going to get oxidized, it must start out poor in H. So it's a lot of words to simply say we have to start out with the NAD version that has no H. So we actually start out with NAD plus. So if I look at that reaction, again, here is glucose that has 1, 2, 3, 4, 5, 6, 7 bonds to O. And you end up with 2 pyruvates, which have 1, 2, 3, 4, 5 times 2. So you're starting out with 7 bonds to O and going to 10 bonds to O. So you've been oxidized pretty thoroughly. The ATP, ADP going in to invest in to get the reaction to go, but you spit 4 out. So you have to put 2 in to break this down, but you get 2 ATP regenerated per pyruvate. At 2 pyruvates, you get 4. So if you've done biochem, you know you have to count how many extra ATP you have coming out. So overall, this is generating 2 ATP, which means it's generating energy. If you were generating 2 ATP, you need to absorb 2 inorganic phosphates somehow. But most importantly, you are carrying out a oxidation reaction. So if this is oxidation for the overall molecule, then this must be getting reduced. You have NAD plus being reduced to NADH. It's gaining an H minus, gain of H minus, gain bonds H, makes it reduction. So seeing the big picture in terms of how bonds H and how bonds O are involved, helpful in OChem, absolutely imperative to understanding your biology reactions. So this, for the most part, is going to summarize pretty much, like glycolysis kind of represents and summarizes pretty much every oxidation you'll see. So let me do a reduction real quick and say, again, it's not the end all be all. There'll be multiple pathways, but learn one really well, like glycolysis. And in this case, a reductive one I want to learn is fatty acid synthesis. We store energy in reduced molecule form because oxidation gives us energy. So reductive processes that build up longer and longer chains will end up storing energy, longer and longer carbon chains, I should say. So I have this compound. You're going to learn this reaction if you end up taking I want to say Chem 311, you'll learn some of it. Biochem, you'll learn probably more of this, but it's what's known as a Claisen reaction to form this. I will worry about next semester, but this is very applicable this semester. We have an ester. It's a thioester with a sulfur. So this is acetyl-CoA here added to an acyl group. So this is aftermath of acetyl-CoA and acyl combining to form a 1, 2, 3, 4 carbon chain. We end up reducing it, but notice we do not affect the ester, but we do affect the ketone, turning it into a secondary alcohol. So this is imperative to note. If we were in OChem, if this was actually an OChem example, if we were in OChem, kind of a weird thing to say during an OChem lecture, but if I was actually focused on the OChem portion of this, I would tell you we need NABH4. It reacts with ketones, but won't interact with esters. So if we use NABH4, we could use it. So NABH4 would work. But we're not. We're going to do biochem. And it ends up, we get kind of lucky. Anywhere I can use NABH4, that looks so much like NAD. D and B are very similar. I mean, I don't know. They look kind of similar, little line right there. So what NABH4 could do, NADH can do the same thing in bio. So what we know in OChem, we can correlate to bio. So NADH actually specifically reacts with ketones and aldehydes. So let me get rid of the NABH4 because I'm playing biochem here. So to carry this out, it must consume an NADH. So an NADH is going to combine with H plus to go to NAD plus because you have used this H right here to go there. And this H plus right here becomes that one right there. So you're going to protonate the carbonyl, and the H from NADH is going to be delivered. Sorry, wrong one. You're going to protonate this carbonyl. NADH is going to send the H into this one, kicks up, and voila, you get that. Overall, you have reduced from a carbonyl to an alcohol. So the organic molecule has been reduced, which means the NADH must be oxidized. If it is oxidized, it is a reducing agent. To be a reducing agent, you have to have H's to give away, so it has to be rich in H. If you can see the big picture of this, it will help immensely in going through a lot of your bio courses. So this is one of those slides, one of those lectures that actually, the second half of this, you probably want to review when you get into some of your pathways, when you get into biochem. So lots of information in this. That's where we're going to tie it off for bio. I do want to actually throw some of the bio questions into the class itself. So those will become fair game in some problem sessions and exams. The one thing I highly recommend you do is go to the book and look at the end of the chapter. There's a table that lists all these different reactions. I would love to click on it, but I don't know about copyright issues because I didn't make it. It's from the textbook. So give a look at your textbook. It's phenomenal for its organization. And hopefully you can, I don't know, just get an overview of what that like big picture of the reactants are. In class, I will go ahead and put it up because we're using this textbook, but I'm just afraid on a video I shouldn't. So I will go ahead and end it here. This is the last for this chapter. Have an absolutely wonderful day, and we'll get into chapter 19 in the next one. And that'll be it for this semester. So it's kind of winding down. So 57 down, I'm guessing about 7 to go. Thank you. Bye.